Hello, I'm Rebecca Barnes, and welcome to the Science ESA vodcast. In this episode, we'll take a glimpse at the hot, energetic, and often violent universe revealed through X-ray and gamma-ray astronomy. We'll look at ESA missions that detect this hidden light and find out how the science these missions perform is meticulously planned. Beyond blue visible light and the ultraviolet region of the electromagnetic spectrum, the waves continue to increase in energy and decrease in length, to about the size of a molecule and then to the size of subatomic particles. These waves are X-rays and gamma rays, energetic and potentially dangerous to life. Due to their extremely short wavelength, X-rays and gamma rays cannot penetrate Earth's relatively thick atmosphere and must be observed by space telescopes. The era of high-energy astronomy really kicked off with the space age, exposing astronomers to violent phenomena that had been invisible at other wavelengths.
Any object heated to more than 1,000,000 degrees Kelvin will begin to give off significant quantities of X-rays. This is one of the many ways that high-energy radiation is produced. X-rays are often detected from a binary star system where one star is extraordinarily dense remains of a stellar core in the form of a neutron star or a black hole. These objects have a huge gravitational pull which strips gas away from the companion star. As this gas spirals towards the neutron star or the black hole, it is heated to incredible temperatures, high enough for X-rays to be emitted. Supernova remnants also emit X-rays, and beyond our galaxy, large black holes are thought to power the tremendous X-ray emission from active galaxies. The gamma-ray universe is a place of constant change, and it can be extremely volatile. Observing gamma rays helps astronomers to understand how matter and radiation interact with each other, especially under extreme conditions where temperatures are hundreds of millions of degrees, where matter is very dense, or where magnetic fields are very strong. Gamma-ray bursts are amongst the most powerful explosions in the universe. They occur randomly and unpredictably. Short bursts are thought to be colliding neutron stars in distant galaxies. Longer bursts may be the very first supermassive stars now exploding as powerful supernovae, known as hypernovae. There is also a diffuse gamma-ray emission coming from our galaxy. This is where energetic particles, or cosmic rays, collide with gas in interstellar space.
Europe is one of the pioneers of high-energy astronomy. In 1975, ESA launched COS-B. This mission lasted for over 6 years and made an extensive survey of gamma radiation across the galaxy. EXOSAT, the first European Space Agency X-ray observatory, launched in 1983, made nearly 2,000 observations of a variety of sources during its 3 years in operation. To continue the venture into the high-energy universe, ESA launched XMM-Newton in 1999. It is the most sensitive X-ray telescope ever built and performs spectroscopy of cosmic X-ray sources. XMM-Newton has 5 X-ray instruments, 3 cameras and 2 spectrometers, as well as an optical ultraviolet monitoring camera. Focusing X-rays is extremely challenging, and for this task, XMM-Newton has 3 novel telescopes that are very different from those used to focus visible or infrared light. The mirrors on board XMM-Newton are barrel-shaped and coated with gold. As X-rays travel down the barrel, they graze the mirror at a very small angle and reflect. If this angle of incidence is too large, the X-rays would be absorbed by the mirror material. Each of the telescopes is made up of 58 of these mirrors, nested together like Russian dolls. This provides the largest possible surface area over which the X-rays are collected. Integral, or the International Gamma Ray Astrophysics Laboratory, was launched in 2002. This observatory studies celestial radiation that is 10,000 to 10 million times more energetic than the photons that reach our eyes from the sun and stars. Integral has a large field of view, allowing many gamma-ray sources to be studied in one single exposure. There are 4 scientific instruments on board the spacecraft. Of the 2 that study gamma rays, one produces images and the other is a spectrometer. The other 2 instruments are an X-ray monitor and an optical camera. Gamma rays cannot be focused by conventional lenses and mirrors, and in fact are incredibly difficult to detect. This is because they are so energetic they can easily penetrate almost anything. For this reason, the instruments on board Integral use a unique technique known as coded mask. A coded mask telescope is like a pinhole camera, but with not one, but many pinholes. Both XMM-Newton and Integral are space observatories feeding astronomers from around the world with fundamental information about the hidden universe. An Earth-based observatory is used by many different astronomers and must be kept in the best condition possible. An observatory in space is no different, but everything must be managed remotely. This is ESA, the European Space Astronomy Centre, the scientific heart of the European Space Agency. It is here, in the quiet surrounds of Villanueva de la Cañada, near Madrid in Spain, that astronomers and engineers work together to study all aspects of the universe. ESA is where the science that the XMM-Newton and Integral space observatories perform is carefully planned. Astronomers from all over the world can request observing time on XMM-Newton and Integral to be used to look at their object of interest. Time on these observatories is highly valued, and both receive enough proposals to fill the available observing schedule many times over. Once the best proposals have been chosen, experts from both observatories meticulously plan what the telescopes will observe and when. To communicate these plans to the observatories in space, the teams at ESA must work with ESOC, the European Space Operations Centre in Germany. From ESOC, the detailed instructions are transmitted to XMM-Newton and Integral via antennae located at various ground stations around the world. As well as planning what will be looked at, the astronomers at ESA play a vital role in receiving data back from these observatories. These data are received from ground stations by ESOC and then sent to ESA, where teams process and store the data so that it can be accessed and used by astronomers around the world. In addition to information about the astronomical observation, data from XMM-Newton and Integral also contains details about the health of the instruments on board and their performance. It is crucial that the astronomers at ESA monitor how the observatories are functioning. If there are any threats to the instruments, commands to protect them can be relayed to the observatory in space. It may sound like the operations of the XMM-Newton and Integral space observatories are a routine affair. However, this is far from the truth. The nature of the high-energy universe is that sources vary with time. An object that seems to emit a steady stream of radiation may have a sudden and violent outburst, or a new source may suddenly start to emit high-energy radiation. These events can disrupt these carefully planned observations.